Okay, in this video, we are going to differentiate between a standing wave and a progressive wave, and that will enable us to revise what a progressive wave is. We'll look at the three types of standing wave. We will talk about something called a harmonic and then represent them as a diagram. So for each of the three types of standing wave, show the different harmonics, and then present each harmonic as an equation. And then, as usual, solve some numerical problems using the three types of standing wave. So what is a progressive wave? Well, it's not this, it's this. This is a transverse progressive wave, whereas the time goes along, the wave travels along, and the maximum displacement changes position. So you could be standing at the beach or standing by a lake, and you'd be able to see progressive waves traveling across the water. And so waves that transfer energy away from the source are known as continuous, traveling waves, or progressive waves. And this is a very important definition. Remember that progressive waves can happen in transverse waves, where the motion of the individual particles is at 90 degrees to the movement of the energy, right? So the particles are moving up and down, right? But the energy is moving this way. Or you can have a progressive wave which is longitudinal, right? So that the particles are vibrating backwards and forwards in the same direction as the movement of energy. So if we have a look at our water wave here, the water waves, this is transverse, the water's moving progressively this way, taking the energy with it away from the source. And so standing waves are very different. Here you can see an example of a standing wave. And what I want you to do is stop the video and have a look at these two demonstrations, right? Where we see a standing wave on a string and a standing wave in water, the picture I've just shown you. And have a look at how they're generated and think about what causes their formation. So stop the video now, watch them and come back. So hopefully you've been able to see that a standing wave has to have an aspect of reflection, right? So a standing wave is the result of a progressive wave that reflects off a surface, bounces back and superimposes. So we've got two phenomena there. Number one, reflection, and number two, superposition. Now let's do a quick overview. When two waves meet whilst traveling through the same medium, they interact and superimpose. Now what does this mean? That the net amplitude of the final wave is the sum of the amplitudes of the individual waves. Again, this is an important definition. Now this can result in constructive interference, which is what happens when a larger oscillation is generated, as in this example. Two amplitudes which are in phase with each other, they create a much larger amplitude. Destructive interference is when the waves superimpose to create a smaller oscillation. Now this is what we call like absolute destructive interference. We're left with nothing, right? But that happens to a degree. It doesn't necessarily have to cancel out completely. You can have some cancellation effects, but in any case, standing waves are generated due to this effect. So the consequence are these areas of huge constructive interference and destructive interference. So we end up with this standing wave pattern. So now let's highlight the main parts of this pattern. We have nodes, which are points where the total destructive interference causes there to be no displacement, and antinodes. Antinodes are points on the standing wave where total constructive interference takes place and there's maximum displacement. Now, let's review this main difference between the standing waves and progressive waves. If progressive waves then transfer energy from the source, then standing waves do not transfer energy, and that's a fundamental difference between the two. If we have a look at this picture here, you can see your nodes and your antinodes clearly. All right, your nodes are represented here and your antinodes by the peaks. Okay, so that's the basic summary of what a standing wave is. So what we're going to look at now are the 3 types of standing wave. Okay, so basically the difference between the 3 types of standing wave is to do with what's happening at the ends, right? So standing waves can be either fixed at both ends. So if you can imagine a string, right, that our standing wave was a string, then the string would be tied up at both ends. The second type would be open at both ends, right? So this was loose and this was loose. I know it's a bit difficult to get your head around it, but I'll try and find some concrete examples in a minute. And then your third one would be loose at one end, but tied up at the other. So we have a fixed at one end, open at one end situation. Now, it's probably better to consider these 3 in terms of nodes and antinodes. So nodes, on your fixed at both ends, you would have a node at both ends and an antinode in the middle, right? And then if you've got both open at both ends, you would have antinodes at either end. And if you've got fixed at one end, you would have an antinode and a node. So let's have a look at some illustrations of this. So here we have our guitar strings. Guitar strings are great because they give us a perfect example of fixed at both ends. If you have a look at the video, you can see there's some standing waves being set up on a guitar string. And in fact, this is how guitar strings work. They're definitely fixed at both ends. But the reason why we're seeing lots of nodes and antinodes is because there's a large amount of standing waves being set up. But here guitar strings, perfect example of fixed at both ends. And this is a visual representation because for open at both ends, what we're really dealing with is wind instruments and longitudinal vibrations. So here we can see antinode, node, antinode, node, and antinode at the end, right? So it's important to be able to visualize that in 3 dimensions. And then here we have our last one, which is fixed at one end and open at the other. So node, antinode, node, antinode at the end. So that's your 3 types of standing wave. Perfect example of 2 open ends in real life are any of these wind instruments where you have basically air columns set up at either end and open here and here in your flute and recorder. The only example I can come up with really that's helpful to visualize for one fixed end is a tuning fork. These are great. So they you can see here that they're fixed, yet the vibration is at an antinode at the top here. Now there is a simulation that you can play with, especially in order to get your head around this idea of a loose end. Now this, as you can see, this end is moving up and down. So that's one way maybe of looking at a fixed at one end. Let's try manual. I quite like that one. That's like lets you play and kind of allows you to think about this idea of having fixed and loose ends. So if I now make this a loose end, this would be a loose end. And it's actually setting up, you can set up a wave which is open at both ends, right? I know it says it's fixed, but it's not really. It won't give you the right pattern. Now, what's nice about the simulation as well is it shows you what happens as you increase the frequency, right? So you have, you kind of fiddle around with it until you get your nodes and antinodes. But as you can see, as you increase the frequency, you get an increased number of nodes and antinodes happening, right? And that's what we're going to look at next. We're going to look at this increase in nodes and antinodes because that's the next step. So the simulation is on slide 160. But let's have a look at the different kinds of arrangements that you get for each of the 3 types of vibration. Now, the easiest form is always called the first harmonic, right? Or the fundamental frequency. So for 2 fixed ends, the first harmonic, which is the simplest form of the standing wave will happen at a set frequency, and the frequency at which this harmonic is set up is called the fundamental frequency, right? In a open at one end, this is what your first harmonic looks like, right? And your fundamental frequency will cause this to happen. Okay, so it's important that you get your head around what this picture looks like. And then for open at both ends, let's have a look. This is what your fundamental looks like. So these are really, really important diagrams. Now, what happens is you increase the frequency from the fundamental. Well, if we go up to fixed at two ends, as you increase that frequency, you increase the number of nodes and antinodes. So this would be your first harmonic, this would be your second harmonic, this would be your third, and this would be your fourth, which is basically a repetition of your fundamental mode of vibration, your first harmonic. Secondly, for one fixed and one open end, again, you get this repetition. Your first harmonic looks like this. Your next harmonic, now careful, right? Because there's a trick here. Your next harmonic is not called the second harmonic. It's called the third harmonic. You cannot get a harmonic in between this. It's impossible to keep the end open. So in one fixed, one open, you go from first harmonic to third and then to fifth. Okay, got your head around that? And then for both open, let's have a look. This is your simplest form, first harmonic, and then you go from your second harmonic and your third harmonic. Always a repetition. So if anything, this one's a little bit easy, a bit more similar to fixed at both ends. But here you do have a first, a second, and a third harmonic. Okay, so those are your harmonic arrangements for the three different types of standing wave. So what I want you to do now, just for 5 minutes, is to spend some time playing around with this simulation, taking some notes. It's important that you take the notes before I throw all the maths at you. Okay? All right, off you go. Do the first part of the assignment and have a play with this thing.